Thanks for attending to our I2PC seminar series on Cryo-EM. This is the first seminar of the series, and the goal of this meeting is to gather users and developers in the same framework with the aim of increasing and make easier their use, as well as understanding the working mechanism behind the methods. That said, let me introduce our speaker. Today we have with us Sjors Scheres. Sjors is group leader at the MRC LMB, and I think he doesn't need presentation because all of us have used Relion. And this is exactly the subject of this talk that I'm sure we will enjoy. So please, Sjors.
Thank you, José Luis. Also, thank you for the invitation to speak. It's a pleasure to be back at the CMB in Madrid, albeit virtually today. And I look forward to meeting all of you again in 3D sometime soon. So today I'll speak about the fourth major release of Relion-4.0, which we went beta with in the just a few months ago in the autumn of 2021. And if you do follow me on Twitter, you'll notice I sometimes rant about how open software accelerates science. And that's because I think that open software developments, like you guys in Madrid do as well, but also like Relion, are very important to kind of keep this field open, collaborative, and that we can all build on each other's advances to make the science go forward as quickly as we can. I thought I'd start with introducing the Relion team as it has been lately. So Takanori Nakane was a postdoc in my lab. He, during the whole COVID lockdown, went back to Japan. He's now working on microelectron diffraction there, but he's still involved in lots of feedback of users and still involved in bug fixes. Dari Kimanias is a postdoc in the lab. I'll speak about his work as well. Li Yidong is a student in the work. I'll speak about her work too. Kirash Jamali is a student who only recently joined. He joined in October, and I will not speak about his work. That's not yet ready, but he's working on automated model building in atomic model building in cryo maps. Then Joaquin Oton, which the guys there in Madrid will know well as well. He was a postdoc with John Briggs, and John Briggs has now moved to Germany to the Max Planck Institute in Martinsried. And Joaquin, or Kino, has moved back to Spain, and he's now at the synchrotron in Barcelona. So Jasenko was a postdoc with me. He's since moved back to Switzerland, and I'll speak about the work that Kino and Jasenko both did on electron tomography. And then Johannes Schwab is a postdoc in my lab who only recently joined as well, and I won't be discussing his work today either. Just like Kirash, it's a bit early on. But he works on deep learning methods to try and deal with continuous heterogeneity in single particle reconstruction. So Relion has also received significant contributions from the group of Eric Lindahl, where Dari was a PhD student, and together with Björn Forsberg there, they did, for example, GPU and CPU acceleration of Relion. And then we're working closely now with a CCPEM group at Harrow in Oxfordshire, and I'll briefly mention that towards the end. And as of late, I'm also working closely together with Alistair Burt, who's a postdoc in the group of David Barford here at the LMB, developing further on the work initiated by Kino and Jasenko on sub-tomogram averaging. Good. New features in Relion 4 come in two different aspects of Relion. We have the first aspect of that is sub-tomogram averaging, and this is mostly work done by Kino and Jasenko, where we have completely re-implemented how we deal with the sub-tomogram averaging inside Relion Refine, which is responsible for 3D classification and 3D refinement. And also, Jasenko has taken his methods for CTF refinement, higher order aberration corrections, etc., and Bayesian polishing into the sub-tomogram averaging arena, and I'll speak to that about that shortly. Then on the single particle analysis side, there's four major developments in this new release. One is a more convenient wrapper to the Topaz auto picker and denoiser, a gradient-driven 2D classification and refinement methods by Dari, automated 2D class selection by Lee, Dari, and also myself, and then automated ways of running Relion unsupervised for on-the-fly processing. I'll start with the sub-tomogram averaging work, and just to mention that traditional sub-tomogram averaging, you would take your tilt series, you would align that. Many people use IMOD for that, and then reconstruct tomograms, perhaps also in IMOD, and then you would identify your particles of interest inside the 3D tomograms, of which you would then window out small boxes, and you would then align and classify those to be able to average over them and get thereby removal of noise through averaging and increase of resolution. Now, this already, we had a workflow for this in previous versions of Relion, and this was work that we did together with Tanmay Bharat when he was in the group of Jan Löwe here at the LMB. And the main new concept of that paper, which was back in 2015 or so, was the introduction of this three-dimensional contrast transfer function that aimed to describe the transfer of signal from the images from the 3D tomograms. This, however, has some problems, and that is because we try to now full Relion with three-dimensional particle images and a three-dimensional, therefore a three-dimensional noise model on these images. But the data that we actually collect and where the actual noise happens is in the 2D projection images of the tilt series and not in the 3D voxels of these sub-tomograms. And that means that it's very hard to make sound statistical assumptions about the sub-tomogram voxels. Also, the effect that the particular reconstruction algorithm has on the tomogram generation is ignored in this process. And thereby also, if you want to take sub-tomograms out of tomograms and you want to do high-resolution sub-tomogram averaging, you have to calculate high-resolution tomograms, which often become huge files, which often hit the limits of what your typical desktop can handle. So it's a practical problem too. So the main idea in the Relion-4 approach is to now use, instead of use sub-tomograms that actually are an approximation of the real 3D reconstructed density, we use pseudo-sub-tomograms where we take the Fourier slices of each of the images from the tilt series and just put them back in a hypothetical 3D Fourier space, and which we call these pseudo-sub-tomograms, and these are explicitly not approximations of the 3D density. And the only reason why we go from a stack of 2D images, and we now take the areas of the 2D tilt series images for each particle, which where they should be in that projection, and put them all back into 3D space. And the only reason not to use the stack of the boxed out 2D projection images, but rather use these 3D images, is a trick, again, for just building on existing code that we had in Relion to deal with 3D volumes. But we now still aim to approximate the likelihood that would arise from just working with a stack of 2D images for each particle, which are then constrained in how they're oriented relative to each other. Now, in order to do so, we went through the math, and it turns out that one thing was missing. We would already kind of have the sub-tomograms in Relion 3 would already have the slices of the 2D projection images and the CTF for each of them. But what we also need is in the 3D pseudo-sub-tomogram space, we need to measure how often each 3D voxel has been measured in the tilt series. And that's because parts of the tilt series images will overlap with each other in the 3D space because of the common line theorem. And we call this measurement of how often each 3D voxel has been observed the multiplicity. So the pseudo-sub-tomogram 3D arrays consist of CTF pre-multiplied experimental images, their Fourier transform, the CTF function of those images measured at each 3D position of the image and a multiplicity for each 3D voxel, how often these images have been observed. Now, the advantage of working with the pseudo-tomograms is that at least this is an approximation. There's a few assumptions, but they're not too bad, to the true 2D problem. And we can just use all the existing methods in Relion for 3D refinement, classification, symmetry, expansion, multibody, etc., without having to do too many changes to the code. And by keeping track of all the geometrical relationships between the particles in the 3D tomograms and how they relate, how they're oriented with respect to the tilt series images, we can then reconstruct for the sub-tomogram averages, not as an average from the 3D sub-tomograms, but actual as a true 2D to 3D reconstruction from the relevant areas of the 2D projection images of the tilt series. Once we have such a high resolution 3D reference, we can also back project that into the same orientations as the particles that we know are in the 2D tilt series, and then refine iteratively parameters about the tilt series themselves. So this can be the tilt series alignment parameters themselves, but it can also be a beam-induced motion that happens throughout the tilt series acquisition, much like we use Bayesian polishing in single particles in movies. You can track the movement of a particle throughout the tilt series acquisition, and also refine CTF parameters that are associated with individual particles, like defocus, or over whole tomograms of all the whole data sets, things related to higher order optical aberrations. To iterate these type of refinements with the actual 3D alignment and classification, you can then iteratively improve 3D maps and get ever higher resolution. So to assist users in using this software, we've made a new GUI, which is launched with using the typical Relion command, but now with --tomo. You get a tomography specific GUI where there is an import function, which Kino has written, where if provided you do things in Kino's way for running IMOD and CTF find, etc., you can then import and start your work from there. And as I'll come back later, we're now trying and make this a better way of actually starting this. Once you've imported your tomograms in the Relion-4 kind of ways, you then generate these pseudo sub-tomograms where you reconstruct these kind of 3D arrays of the CTF pre-multiplied images, the sums of all their CTF squares and their multiplicity. And you write out all these pseudo sub-tomograms, which can then be fed into any of these 3D initial model, 3D classification, or 3D auto refinement. And this will then align the particles relative to a common reference frame. Once you've done that, you now have a high resolution 3D reference structure, which, as said, can then be used to do the alignment. You could realign the tilt series, and that's done under the polish tab here, where if you set fit per particle motion no, all that you're doing is kind of optimizing the tilt series alignment that may have come from IMOD to best fit the projections of each of the individual particle images into the tilt series. And if you set fit per particle motion to yes, then you'll be doing something much more akin to Bayesian polishing, and you'll try to follow the motion of individual particles throughout the tilt series acquisition for the entire tomogram. Likewise, you also have a tomographic version of CTF refinement, and this is again is akin to what happened before in single particle analysis as well. You can refine the defocus of individual particles, and that in itself will probably be advantageous for your resolution. You can usually get, even at medium resolution, get quite good improvements there. And if you also on the aberration tabs refine odd and even aberrations, then you can do higher order aberrations like coma, etc., which may result from you not having aligned your microscope very well. And that, I would say, is only useful if your sub-tomogram averaging actually goes to significantly higher resolution, often below 3 angstroms resolution. That's not in itself so useful. So this then provides you, as said, with a mechanism where you can iterate through the data, you realign them, you optimize the foci, aberrations, particle motions, etc., and then you make new pseudo subtomograms which you realign, etc., and you until this no longer improves. So we've written a preprint on this, which you can find on bioRxiv, and we're still working on writing up the paper for publication. And the fact that Kino and Jasenko is no longer with us is kind of is causing some troubles, but hopefully we'll get soon to a submittable stage of the paper, and at which point we will also update the bioRxiv version. But one result already mentioned on bioRxiv is this immature HIV test data set from the BRICS lab, which has been used by many different people. And going through 3 cycles of this refinement, and then CTF refinement and frame alignment, particle motion correction, we get to a resolution from only 5 tomograms to 3.2 angstroms, which is as good as it gets with any of the existing methods out there. Now, I think the import things that were written by Kino and which are currently on the Tomo GUI are still apt for a lot of improvement. And if you don't use IMOD exactly in the way that Kino had envisioned, then this is causing problems for people. So we're continuing to work on this, and this is the work I mentioned earlier with Alistair Bird from the Barfoot lab. Alistair has written an import function that just starts from raw movies and raw serial EM MDoc files that come from your data acquisition experiments, which get imported. You form these kind of tomograms.star files as Jasenko had envisioned, on which you then have modified the CTF find runner and the motion core runner in Relion, and you can now run CTF find and motion core on these raw tomogram.star files, which come straight from the import from Alistair. From there, Alistair has written a nice wrapper to a line-tailed series of individual tomograms in IMOD, either through fiducial-based alignment or patch tracking. And this is now also accessible. This will become accessible through the GUI of Relion in a line-tailed series type of job type, where you can run IMODs from the Relion GUI. And then we use Relion Tomo Reconstruct Tomogram program to reconstruct all these tomograms. And then Alistair Bird, who's a strong proponent of the Napari software for visualization, is currently working on pickers, just manual picking of individual coordinates, but also things on geometrical shapes like spheres and cylinders and so on will be hopefully all part of this. And all that combined will hopefully in Relion 4.1 provide an entire pipeline from raw experimental data all the way to a high resolution average, very much like is the case currently with single particle analysis, hopefully thereby removing some of the burdens which currently still exist with people who want to move into the pipeline. Cool. So in terms of single particle analysis, as I said, for new things, one is the Topaz wrapper. This is something I wrote myself. So this is based on Thurston Bappler's paper from Bonnie Berger's lab, and Alex Noble has been much involved with this software as well. So they have this positively unlabeled convolutional neural networks, where you train a neural network by picking a few of the particles in the images, and then the Topaz will automatically pick the rest for you. There's also a pre-trained network that has been trained on many different data sets, which you could use and might be good enough as well. So the Relion, besides that, there's also a micrograph denoising option in Topaz, and that comes with a pre-trained network, which you can now run from the manual picking job type, which you could already kind of low and high pass filter your maps just to your micrograph, so just to facilitate particle picking. But you can now also just use Topaz denoising using the pre-trained network that they provide. Just to give you an example, this is a raw micrograph from, I think this is beta-galactosidase from the Relion tutorial data, and this is how Topaz denoising works on that data set. So the auto picking now has a new tab called Topaz here, where you have to provide where your Topaz installation is, and then you can either perform training by manually picked coordinates that you've selected in the manual picking auto job type, or you can train on a set of particles, for example, because you've log picked initially your data set, you've done 2D classification, you've selected only the best particles, and now you would like to train your Topaz network to really find all the best particles in your data set. You can use this second option here. You can either do Topaz training, or if you already have pre-trained, you can say perform Topaz picking here and give the pre-trained model, or if you say perform Topaz training picking yes, but you don't provide a model, then it will just use the pre-trained model that Topaz ships with itself. Just again, an example from the BTGAL dataset. This is what the Laplacian of Gaussian picker in Relion does, just basically finding blobs of the right size, and you will have some false positives here on some of the contaminations. And this is what Topaz picks, and here blue means better, and the redder the particles are, the lower confidence Topaz has in these particles. So you see some of the false positives are avoided, and probably this one's still a false positive there. Now, I would say probably the biggest advance on the single particle analysis side is a new algorithm by Dari, where we used gradient-driven approach, but now with explicit regularization. And gradient-driven approaches in cryo-EM single particle analysis were spearheaded in the field by Ali Punjani in CryoSpark, and they proposed this stochastic average gradient descent algorithm, for which they then obtained patents. And we initially had implemented those algorithms in Relion, but then we got in trouble with the MRC lawyers, who were worried about the Structura patents, and they made us rip this out. So Dari has now written a new algorithm, which is based on ADAM rather than SGD type, SAGD type optimization, which kind of circumvents some of the patent problems. So everybody can now use Relion again without worrying about Structura, even if you're an industrial partner. And again, I would stress that if you keep your software open and unencumbered by patents, then it's much easier for other people to accelerate science altogether. Now, the main difference, I would say, from Dari's approach to anything that was out there before is that Dari has found a way to also regularize the 2D class averages or the 3D maps that you get from the gradient-based approach inside the kind of Bayesian framework that Relion lives in, because that's kind of one of the downside of the SGD algorithm is that, yes, well, upsides are you go faster, you do subsets, and you have potential global optimization properties of the algorithm. But downsides are that because you don't iterate over the entire data set anymore, you can't really calculate explicitly by how much you should regularize, by how much you should filter the references to keep noise at bay. And therefore, SGD typically relies on kind of ad hoc regularizers, which kind of just keep noise at bay, but it's not testing how much noise there is and then optimally filtering the references at each iteration. And this is what Dari has figured out in his algorithm, which we called VDAM, and I think that's one of the main advantages there. Another thing that the Dari's algorithm does is when classes start to collapse into each other and some classes become empty, which happened to the EM algorithm as well, Dari kind of explicitly splits them up again and respawns new classes, which results typically if you do 2D classification with the VDAM algorithm, you get many different classes, which many of the users seem to like. So you typically run about 100 iterations of the VDAM algorithm, because each iteration sees now a much smaller subset of the particles than the 25 full data set iterations in EM algorithm. The whole VDAM approach is typically much faster. The larger the data set, the faster relative it becomes, and typical speed up factors are about 6 or 7 fold or so. So just to show an example on a data set that we tested this on, up here is results from a typical EM 2D classification. I think equal number of classes were used as in the VDAM algorithm shown here below, but because many of them collapse to empty classes, you can see there's much fewer 2D class averages that are useful than for the VDAM algorithm. And if you look in detail, the VDAM algorithm will have found some views which were probably kind of hidden between averages of multiple views from the EM algorithm. And this is just another example of that. Now, with all these 2D class averages, in the standard workflow of people, you would then look at the 2D class averages and select the good ones and select particles that were assigned to the good ones to then move forward to 3D refinement. And we've always found that 2D classification was a very efficient way or a very effective way of cleaning up the data set and selecting the best particles to move forward. However, if you want to do automated processing on the fly, because you don't want to, then you don't want to sit there and select good 2D classes. So that was to automate that process was Lee's PhD project, and then Dari and myself helped things over the finish line in the end. So what we did, I made a little hack in our local installation of Relion at the LMB, and over the period of 3 years, whenever people performed a 2D or a 3D classification, I asked them, would you like to share the results with the developer team to develop better software? And many people clicked yes when they did that. So we collected a few, well, several hundreds, perhaps even a few thousand of 2D classification runs. And from these, Lee then sat down for quite a long time to go through these and clean it all up, make sure not too many of them are ribosomes or beta-gal, etc., kind of have a good separation of different targets. They're all from the LMB, but there is many groups here. There's about, I would say, probably 20 to 30 different groups working on different types of proteins. So we now have the total result of this work is that from 3 years worth of 2D classifications, we've now selected almost 15,000 2D class average images that then Lee sat down and interpreted all of them on a continuous quality scale, ranging from 0 being very bad to 1 being very beautiful 2D class averages. And what we then did, we developed a convolutional neural network to take the images and try and reproduce this score on a training set. And we don't only use the images themselves, which are downscaled to 64 by 64 kind of common size. We combine the image information itself with features which get extracted from the metadata mainly of the Relion 2D classification. And these contain data that are not, these also contain data that are not in the images themselves, like how many particles have contributed to this class, what's the resolution of the class, what's the rotational alignment accuracy that Relion estimates, the translational alignment accuracy, etc. And some other features which are calculated from the images themselves. So the combination of the images and the features we found to work best, and this is kind of a confusion matrix. So these are labeled scores and these are predicted scores by the network. And this is just to give you an example. So near 0, you have classes which we typically find useless, and then higher value classes are more beautiful class averages. So this is now available through the subset selection. So this is the job type you would normally launch to do the manual selection, and on class options tab there, you can now automatically select 2D classes to yes, and you can define the threshold that you want to apply this selection for. So only select, for example, here classes that are better than 0.5, and then you will need a conda environment. We kind of reuse the conda environment we have for Topaz anyway, because you need to do the neural network execution is done actually in Python. Now, the selection you want to use, that we feel is a parameter the user still needs to tune. And the reason for that is that if you do 2D class selection of ribosomes, you may have a much more stringent criterion than if you do 2D class selections of a very small membrane protein, which it's quite hard to get good class selections. So to reflect that, you would put for ribosomes perhaps a value of 0.7 or so, and for the small membrane protein at the initial stages of processing, you might want to go down all the way to 0.1 or 0.2, etc. Now that's reflected here. So we applied this automated class selection to 12 data sets. Importantly, these were data sets that we selected before the project started. So these are not kind of cherry picked and looked at later. And you can see for where we compare now manual selection, this is the number of picked particles from as a percentage from all the auto-pick particles, manual selection, and then with the class ranker, this is the program for the automated class selection with the fixed threshold in orange, or a user-determined threshold in purple. And then we have false positive and false negative rates, where we compare how does automated class selection perform relative to a supervised expert manual selection of the same 2D class averages. And especially if you use the user-defined class threshold, which the actual value for this threshold is here. And so this, for example, for the ribosomes, it's set at 0.5, but for some of these more difficult data sets, we go much lower in the threshold. And then false positive and false negative rates are typically 0.2 or better. So we think this is now good enough to incorporate in fully automated 3D reconstruction procedures where we do use 2D class averaging as a means to select the best particles. And to facilitate that further, we've improved something that was called schedules in the old Relion and is now called schemes in Relion-4. And in the old Relion-3, we already had Relion-it.py, which was for automated processing, which is now re-implemented to work with these new schemes. And the schemes are basically a Relion-specific little way of going through possibly branched graphs of predefined jobs. For example, for fully automated structure determination, we have two schemes that we distribute with Relion, also as an example of what can be done. But the whole scheme network is meant to be flexible and relatively easy to program, so that if you have a specific need for automation yourself, because you do have a specific problem that is different from normal 3D reconstruction, you can write your own schemes and do this also together with your hardware and your setup there. So the kind of standard scheme, the one is preparation and the other is processing. The pre-processing, there's a loop where you do waiting, and then after, for example, a day, it will just give up. But it will basically import all the new movies and run CTF-find and motion correction on them iteratively. And then in parallel, we launched this scheme called proc for processing, which has a loop as well. And it's have you done CTF-find on any of the micrograph? If that's no, it will just keep on waiting until this is the case. If it's yes, then we're going to select micrographs based, for example, on the resolution estimated by CTF-find. And we're going to count how many we have, and if we have more than the previous round, if we have not more than the previous round, we just go back and wait until we're more. But if we have more than before, then we auto pick with the log picker typically, or with the Topaz. You can set this up as you want. Then do 2D classification and select all the good particles, and then count particles and see, do we have enough to go into 3D refinement or not? If not, we just wait and see until we get there next time. If we do have enough, you can either provide an initial reference, or the thing can do this for you. This is another branch here, and then do 3D refinement. So this is kind of a standard scheme. It will keep the resolution of everything low in order to gain speed. I think by default we keep things to 64 by 64 pixels, but you can set this up as you want through the GUI. And this is then this GUI of the Relion Immature.py scheme, where you have the settings for pre-processing, where are your movies, what's the gain correction, the voltage, some experimental details, etc. How does your particle look like? How big is it? What symmetry does it have? And then, what's the resolution for my micrographs? Do I want to use Topaz? What model do I want to use? Or do I want to use the log picker? And what score do I want the 2D classes to have, and how many particles do you want at least to do a 3D refinement? So this, you just hit save and run. This will launch the job, and then it works together now with another piece of software which was written by Grigory Sharov, and the people in Madrid will be familiar with Grigory because he also works a lot with the Scipion team. He's written this Mdcatch, which can work with both Scipion and Relion schemes as well, so where you automatically grab metadata from EPU or CREM sessions from the microscope, just pointing to the path of the directory where your data acquisition is going on. And then it runs, if you select Relion here, it runs the schemes with either Cryolo picker, that's something Grigory implemented, Topaz picker, or the log picker, and it basically does the same thing. So the Relion schedule GUI, you can follow what all these jobs are doing. You can abort it, you can stop it and reset at any point. And that's a major advantage over the old schedules, is that this will kind of keep track of what you've done so far. And if something goes wrong or you change your mind about certain parameters, for example, in the 2D classification or the selection of 2D classes, you can just stop this without having to redo everything, which was the case before. You can just set up you can restart this at the position where you want to restart, for example, a new 2D class selection with a new threshold, and it will keep all the previous jobs that are not affected, but it will just redo all the downstream jobs that are affected. Things like that are major advantages of the schemes as opposed to the previous schedules, which were more rigid in that way. So we then applied the whole scheme to the 12 data set I mentioned before, and for 11 of them you get great 3D reconstructions completely automated from the raw movies without any user intervention, just using default parameters that you give on this Relion.py GUI. The only advantage, the only exception is there's one data set that didn't work, and that's kind of paradoxically is the one that could yield the highest resolution, which was apoferritin, and there kind of the picker and the 2D class selection fail rather miserably, probably because the data set that we chose before we started all this was from the FreeAlign tutorial, the system tutorial, and the particles are very tightly packed together, and some of the things fail there. But if you would tweak with it, you would probably make that work as well. Cool. Nearing the end, just to mention that we are now working very closely with Tom Burnley and Colin Palmer at CCPM, and specifically also with Matt Yadansa, who's doing a lot of work to now take the Relion-pipeliner, which has these star files of all the processes and the nodes between the processes, and which keeps track of the history of your entire project of Relion. Matt has taken this, made a re-implementation of this in Python, and has expanded it to also contain other types of job from the CCPEM-pipeliner. So he's now expanding this to CUT jobs and RefMac jobs, etc. And this is partially funded by global phasing from Gerard Bricogne. And the vision here is that together with a new GUI that is being developed for CCPM, which will sit on top of this CCPEM-pipeliner, you can now go all the way from, you can hopefully soon go all the way from raw cryo movies to not stop at the post-process map in Relion, but you just continue through in one CCPEM-pipeliner to model building, model refinement, model validation, and ultimately even submission to the databases. Being in one entire framework, all the metadata will be stored, and hopefully there will be then submission scripts that allow you to upload all of this, and then hopefully make EMDB and PDB submission a lot less labor intensive. We recently did a project where Sophia Leuvenstam in my lab solved 76 structures of amyloids in one project, and she did 30 submissions to EMDB and PDB, and that in itself was a lot of hours work for Sophia, and hopefully by keeping track of everything we do in one big framework, we can make this a lot easier. Cool. Just to mention that we've moved most of our documentation over. There's still a bit pending from locally hosted wiki pages to read the docs, so you can now go around read the docs. There's this button here at the bottom which you can change from 3.1 to 4.0. 4.0 is still in beta, but we'll hopefully soon we'll go stable with this, and then that will be the default that gets loaded as well. So you will find the tomography tutorial from Kino and Jasenko here as well, besides the familiar single particle tutorial. Cool. That was it. Thanks again, all the wonderful people I have the privilege of working with. I also thank Alistair Bird. I should have grabbed a picture of him and put it on here, but I didn't have time to do so. I thank Rafa Leiro, who's at the CNEO there in Madrid, for a lot of early testing, especially with the schemes and the automated processing. I thank people here at the EM facility, Giuseppe and Gregory, especially for their help with implementing on-the-fly processing now here at the LMB. CCPM and Global Phasing for this project that we now have going forward together. I hope in a few years the Relion GUI will no longer have a need to exist, and we will all use a much fancier CCPM GUI and live in a much bigger framework there. And then our high-performance computing systems here in the lab are maintained by Jake and Toby, and we really need those machines to do our work, so I'm grateful for them too. And I thank you very much for your attention.
Thank you, Sjors, for this great talk, and I hope all of you could enjoy as I did. I see people writing in the chat. If you have any question, you can write, or you can also use the microphone icon and directly ask. Meanwhile, I will read the questions. Carlos Oscar Sorzano asked, hi Sjors, is the ADAM gradient algorithm also working for 3D refinement and classification?
Yes, hi Kos, great to see you here. Yes, so this is works both in 2D and in 3D. In the paper, I think we briefly mention it, but we don't show many results with the 3D. It's slightly less tested yet. But for example, the initial model generation is always done using the VDAM algorithm now. And that is mentioned in the paper, and all the automatically determined structures that the 11 that I showed at the final, one of my final slides, they were all done using the VDAM algorithm for calculating the initial model. And the advantage is because you no longer have to ad hoc regularize them. In the SGD, we would always kind of keep resolutions low in order to prevent the buildup of noise. Now you can just let the VDAM algorithm find out what the resolution is and push some of these initial models straight away much further than the, I don't know what the default was, 20 or 30 angstroms that we'd put on the previous versions of the SGD. So yes, it does work. Also for 3D refinement, there things need to be tested a bit more. So there's more you can do when you have two half sets in the 3D refinement. And that's, I'm not entirely sure Relion-4.0 handles completely correctly, but yes, 3D classification for sure it does.
Thank you. Well, you can see the questions in the chat.
Yes, then I can see Bernali, well, relaxed symmetry produces a message. So relaxed symmetry wasn't done by ourselves. I think this was a pull request from somebody else. And then there was it? Yeah, I think from people from Huiskenen's group. Did I see, who was the person here? Did I see that person in the list?
Bernali Bau.
Serban. Yes, Serban. Did I see Serban's message here? Yes. I know there was I'm not entirely sure. I'd have to check what the current status is, but there was a problem with certain point group symmetries not working well. But it sounds like the not a valid Relion argument is probably a little bug. I'll have to look into it.
There are more questions. One from Shiwei Su, and says that the Relion-4
Oh,
deals.
yes, I can see. Shall I read the question, José Luis? Relion-4 deals with subtomo through pseudo-subtomo 2D images stacks. I'm wondering if it can process tilt series collected only at 3 angles, such as plus and minus 30 and 0 degrees. Yes, you can. And I think that's an exciting avenue to explore. So, if you guys would be interested in doing that, I would definitely invite you to try and use Relion-4 for that. Now, we discussed this with John Briggs here, and John is quite keen that we do make a full 2D version of the code where you process stacks of 2D images rather than the pseudo sub-tomograms. And the main reason for that is this user case, because it would be much cheaper computationally to process 3 images that are 2D as opposed to 1 full 3D image. The number of operations you would have to do would be a lot lower. But under the assumptions we make, we do think that the 3D approach that we currently have would be equally valuable, albeit a bit slow, for doing only 3 image tilt series. So this is definitely something you could look into. And if you do, let me know how it works. I would be very interested. Shall I take Ernesto's question as well, José Luis? Perhaps that's easy.
No. I think it's much better if you read it and
okay.
You can...
Ernesto says, in the VDAM algorithm, is it possible to change the number of particles that are processed in each iteration? Regarding the previous EM algorithm, would it also be possible to discard the empty and expand the number of different classes? So the way, let me first do the second part of the question. The way the expansion of the number of classes is done actually depends on the gradient. So you wouldn't be able to do it in the same way. You could probably write something else, but we haven't done that and haven't tested it. So in the EM algorithm, you can currently not do this. The change the number of particles that are processed, I think there is a way to. I would have to check actually on the. I think there is an overall parameter you can already give on how big the subsets are, but I'm not sure if it's exposed on the GUI. So yes, you can change this, but there is some heuristics insight on how quickly do you grow these classes. And I would have to check on the command line arguments which ones exactly they are to control this process. But yes, this can be from the command line, probably not from the GUI, can be controlled. So Serban, I'm reading. Serban is here, so if he knows what the status of the relaxed symmetry. Oh, there is symmetry doesn't work at the moment for non-cyclic symmetries, but I don't know what's causing the not a valid. Yeah, so I think, however, look, that warning is probably my fault. It's probably a bug.
Well, it seems that there are no more questions. I just want to ask you, it's something very general, but I think it's useful, at least for all of us that we are developing algorithms. Recently, with all advances in tomography, that the particle per tilt and the use of tilt series instead the pseudo sub-tomograms, I wonder what do you consider that should be the next step or the next advance or significant advance in at least in tomography?
I think you could think of doing 2D stacks type of program, especially if people move to fewer images per tilt series, which could have important advantages. Then that might that could be faster, and you wouldn't rely on some of the approximation that we're using now, although I don't think they're very bad. But besides that, I think it would be improvements in. There are certain things we, for example, don't do that Dmitry Tigonov does, which I think would be interesting to do. So he uses this, you can combine motions, etc., and the estimations for multiple different types of particles in one tomogram. I think that's quite a powerful thing to do. So that's something we would probably want to do in the future, and just having those, that's where the main gains are, I think. Following motions, perhaps include rotations, etc., not only translations. In the whole tail series against the 2D images, there is still improvements to be had, and I think Dimitri is probably the ones who's furthest along in those lines.
Okay, it was curiosity more than
a
technical question.
With Dimitri's staff, and also I think there's other programs now. What's it called from Ben Himes? The program
EM Clarity.
EM Clarity and Relion-4. I think we're firmly into a next stage of tomography, and you can already start to see this, where you get way better structures out than before. So I think that's, you'll see in tomography similar things than what happened, with before and after Relion for single particles. So you will, and Dimitri has been probably among the first to show this, really what you can do. So I think for fields, I think this will now, you'll see a lot more, much better sub-tomogram averages. They have always been quite blobby, etc. And suddenly you'll start to see a lot of sub-tomogram average structures with beautiful main chains, but even lots of side chains, I think, will be coming pretty soon. And what I hope, with our pipeline in Relion-4, especially what we envision now for 4.1, we hope it will also be a lot easier for people to get into these pipelines as it was before, because I think the tomography field there's a lot of ad hoc scripting by a lot of different people in lots of different ways that have been going on. And if we get some standardized pipelines which give very good results, then I hope it will be accessible to a lot more groups than now.
Yeah, it's much richer and complex. Yeah. Well, thank you.
Cool.
I don't know if there are more questions. Seems no. There's someone typing, but people is saying that this is close. Okay, so thank you, Sjors, for this great talk. We, all of us, really appreciate that you stay here.
Yeah, it was great fun. Good questions. Thanks a lot for inviting me, José Luis.